Level 0. A radio operator in the 1950s is scanning shortwave frequencies for nothing in particular when the dial catches on something. A falling note, then another. A whole chorus of them sliding downward like birds calling into a canyon with no floor. He isn't picking up a broadcast. He is listening to space itself, and the source is a bolt of lightning that struck the ground thousands of kilometers away, minutes earlier. This is the Whistler. The pulse from a lightning strike escapes the atmosphere entirely and rides Earth's magnetic field lines like a marble in a groove, arcing out past the ionosphere before dropping back down on the far side of the planet. Higher frequencies arrive first, lower ones drag behind. An instant crack of thunder gets stretched into a full second of falling tone. For years, wartime radio operators mistook these for coded enemy transmissions. It took decades before anyone realized what they were actually hearing. Nothing sinister, just weather, echoing. That storm happened once. Earth is still humming from it. And this is the gentlest thing on the entire list. Level 1. 20,000 times stronger. That's Jupiter's magnetic field compared to Earth's. And it doesn't sit quietly. It grabs charged particles from the solar wind and the volcanic moon, Io, spins them into a radiation belt lethal enough to fry an unshielded spacecraft in hours, and that belt broadcasts. When Voyager 1's plasma wave instrument caught it and researchers shifted the frequency into human range, this came out. Not one tone, a wall of them, layered, some pulsing to the planet's 10-hour rotation, some just hissing without pause. This is Jupiter's radio roar, known scientifically as Jovian decametric radiation. It's loud enough that a backyard antenna on Earth, 628 million kilometers away, can still pick up bursts of it. Most of that loudness traces back to Io, dragging its own magnetic field through Jupiter's like a wire scraping a live current, flinging volcanic material along field lines until it slams into the poles and lights up auroras larger than our entire planet. Astronomers can roughly predict when the worst bursts will hit, based on where Io sits in orbit. A moon is driving punishing electric currents through its parent planet's magnetic field. On a schedule we've learned to read. One moon, dragging its field through a planet, does that. The next planet on this list has an entire ring system doing something to it, and the sound isn't shrieking at all. It's closer to singing. Level 2. You'd expect two gas giants with strong magnetic fields to sound roughly the same. They don't. What Cassini picked up from Saturn in 2004 sounds almost deliberate. A cry that climbs and falls in pitch, closer to something alive than anything mechanical. This is Saturn's cry, known scientifically as Saturn kilometric radiation. It's produced by electrons accelerating along field lines near the poles, the same basic mechanism behind Earth's auroras, just scaled to a planet 120,000 kilometers across. Researchers noticed the pitch rises and falls in exact rhythm with Saturn's auroras. The sound and the light are the same event, recorded through two different senses. Then astronomers noticed something even stranger. The rotation period behind that whale seemed to drift over months and years, as if the planet were slowly changing its own voice. It took a long time to land on an explanation. Seasonal shifts in the upper atmosphere altering how the radio waves get generated in the first place. A planet quietly rewriting its own broadcast schedule for reasons we're still confirming. But every planet on this list, every scream and every whale, is happening inside something far bigger. Something that hasn't made a sound yet on this video, and it's the one thing all of them orbit. Level 3. The sun should be silent. It isn't. Helioseismologists discovered it's ringing constantly, pulsing in millions of overlapping sound waves trapped inside a star with no solid surface to escape through. The photosphere rises and falls by mere meters across cycles lasting minutes to hours. Compress months of that oscillation into seconds, shift it up into audible range, and you get this. This is the sun's hum, its measured solar oscillation. A deep tone humming like a cathedral organ holding one impossible chord? The sun's dominant note sits around 235 nanohertz, so a single wave takes roughly 5 days to complete one cycle. To hear it at all, scientists speed the data up tens of thousands of times. Now the reframe. Every whistle, scream, and wail so far has happened inside the sun's own magnetic bubble, the heliosphere, roughly 18 billion kilometers across. The sun isn't another entry on this list. It's the room every other sound has been happening in. and solar flares send pressure waves rippling through the star's own body, sometimes visible as expanding rings on the surface, like a stone dropped into plasma. Some researchers still debate whether faint acoustic traces of these events arrive at the far side of the sun before the visible flare does. If a star's resonance can outrun what we can see, what happens the moment we point instruments past our own solar system at something that was never built to transmit at all? Level 4. What if the universe had built a perfect clock, then buried it inside a corpse? In 1967, graduate student Jocelyn Bell Burnell was reviewing chart paper from a radio telescope when she found a pulse the equipment shouldn't have been capable of producing. Tick, tick, tick. Every 1.337 seconds without fail. The team nicknamed it LGM-1, Little Green Men, because nothing natural should tick that precisely. For weeks, they couldn't fully rule out an artificial signal. This is the pulsar's tick, from what we now call a pulsar. It's a collapsed star roughly 20 kilometers wide, spinning fast enough that its equator moves at a meaningful fraction of light speed, sweeping a radio beam across space like a lighthouse. We only detect it because that beam happens to point at us. Countless others sweep beams that never touch Earth at all, invisible forever. Some pulsars are stable enough to rival atomic clocks. Others glitch unpredictably, suddenly speeding up as if something inside a dead star shifted its footing. Trained scientists briefly considered they'd found something intelligent. They hadn't. The universe had accidentally built something that could imitate one, using nothing but gravity and leftover spin. A dead star ticking with more precision than most machines humans have ever built. Level 5. 13.8 billion years. That's how old the sound you're about to hear actually is. The cosmic microwave background is leftover radiation from roughly 380,000 years after the Big Bang, the moment light first traveled freely. It fills every direction you could point a telescope, carrying temperature ripples of mere millionths of a degree, the exact blueprint that grew into every galaxy, star, and person who has ever lived. Those ripples were real pressure waves, physical sound moving through the infant universe's plasma before atoms had fully formed. Cosmologist John Kramer converted the data into audible frequencies, and this is what came out. This is the Big Bang's afterglow, the sonified cosmic microwave background. A deep swell, rising and falling like something enormous breathing for the first time. It hasn't stopped arriving. Every second, more of that ancient light reaches Earth from slightly more distant regions, because the universe is so large that light from its farthest visible edge is only getting here now, 13.8 billion years after it left. You are sitting inside the echo chamber of your own origin. It never stopped ringing. It's just too spread out, too quiet, for any single instrument to catch more than a fragment. The birth of the universe left behind a sound this large. Two of its most violent objects colliding leave behind something faster, sharper, and over in less than a second. Level 6. For a century, physicists doubted this could ever be measured. Then, for 4 milliseconds, they were wrong. On September 14, 2015, two detectors 3,000 kilometers apart caught the same signal within milliseconds of each other. This is the merger chirp, the sound of gravitational wave event GW150914. A quick rising chirp climbing before cutting off. Two black holes, roughly 36 times and 29 times the sun's mass, had spiraled into each other and merged in a fraction of a second, radiating more energy in that instant than every star in the observable universe combined, as pure gravitational waves rather than light. The event happened roughly 1.3 billion years ago in a galaxy far outside our own. The ripple it caused stretched the detectors on Earth by less than the width of a proton, after crossing the universe for over 1 billion years to get here. Some scientists on the team assumed at first it was a planted test signal. A real detection this clean, this early, seemed too convenient. It wasn't planted, it was real. More black holes are spiraling right now. Their chirps are already crossing the universe toward us. We simply haven't built enough detectors to catch most of them. But what does a black hole sound like when it isn't merging with anything at all and just keeps going for billions of years without a single pause? Level 7. Somewhere in the Perseus galaxy cluster, a supermassive black hole has been holding a single note since before most of Earth's continents finished arranging themselves into their current shape. Unlike everything else on this list, this one isn't translated data. It's an actual pressure wave, moving through real gas, the same basic mechanism that lets you hear a voice across a room. It sits roughly 240 million light-years away, pumping energy into superheated gas for at least 2.5 billion years, sending ripples outward that NASA's Chandra X-ray Observatory has photographed directly, frozen rings on a pond hundreds of thousands of light-years wide. Researchers calculated the pitch, roughly a B-flat, 57 octaves below middle C, millions of billions of times lower than anything a human ear could register. Shifted up quadrillions of times into audible range, it becomes this. This is the black hole's note, sonified from the Perseus galaxy cluster. A low, ominous drone, less like a note and more like a planet groaning. This isn't an echo from the past. By every model astronomers have, that note is very likely still sustaining, right now, at this exact moment. One held breath, unresolved, for 2.5 billion years and counting. Nobody knows when it ends or if it ever does. And if a single black hole can hum for that long without pause, what's still out there that we've never once managed to catch at all? Level 8. On December 27, 2004, a burst of radiation crossed 50,000 light-years of empty space, hit Earth's upper atmosphere, and compressed it. Instruments on the night side of the planet, the side facing away from the source, registered a spike in ionization within a quarter of a second, as if the sun had briefly risen in the wrong place. The source was a magnetar, a collapsed star with a magnetic field so extreme it can warp the shape of its own atoms. In about 1/10 of a second, it released more energy than the sun produces in roughly 250,000 years in a single starquake violent enough to crack its own crust. This is the MAGNETAR'S scream, from the SGR 1806-20 giant flare of 2004. A sharp, overwhelming spike followed by a long, fading pulse ticking at the star's own 7.6-second rotation, the sound of a dead star's surface still ringing after the crack that broke it. If that flare had happened a few thousand light-years closer, some researchers have estimated it could have stripped a meaningful fraction of Earth's ozone layer. Instead, it arrived from 50,000 light-years away and still left a measurable mark on our atmosphere in under a second. 3 of these giant flares have been caught in the history of human instrumentation. The rest of the galaxy's magnetars are still out there, quiet for now, until the next crust gives way.